So good morning, everybody. Welcome to this new BioCOGEN 2030 webinar. My name is Giulio Poggiaroni from EUBIA, and today we'll moderate this webinar called Biomass CHP in the Clean Energy Transition. So today we will have debate focused on the role of bioenergy and cogeneration in Europe, especially in the context of the Fit for 55 strategy. And then we will have two presentations from the Blaze project and the SmartCHP project, who are two Horizon 2020 research and innovation actions currently under development, which are developing biomass CHP solution on the field. And then at the end, we will have a quick session, quick interactive session with Q&A and debate among our speakers. So two quick words on BioCOGEN 2030. This is an initiative launched last year between the Blaze project and the SmartCHP project. It's the aim is to develop a small community of stakeholders active in the field of biomass CHP. We say small because we perfectly know that cogeneration from biomass is a very niche sector, but we have reached so far a nice degree of attention from the audience that we aim to reach. So without further speaking from my side, I will introduce the first speaker for today, which is Alexandra Tudoroiu from COGEN Europe. Welcome, Alexandra. You can switch on your camera.
Good morning, everyone.
Good morning. So Alexandra is head of policy at COGEN Europe, and she will talk us about the role of cogeneration and biomass cogeneration in Europe. So the floor is yours.
Indeed. So let me share my screen. So okay. Everyone should be able to see my slides now. And thank you very much for the invitation to speak today. So just a few words about COGEN Europe. We are the cross-sectoral voice of the cogeneration industry at European level. As an association, we are a hybrid more or less. We actually represent both national associations and corporate members. 14 national associations from across Europe, as well as corporate members ranging from manufacturers to utilities to industrial users of CHP and to energy service companies that actually develop CHP projects. When it comes to the manufacturers, we also represent a broad range starting from the kilowatt to the megawatt. And so in our portfolio of technologies, we do represent bioenergy-based CHP and all sizes, from the micro CHP to large-scale CHP and to commercial CHP as well. So what is our vision? A few years ago, we actually gathered our membership to develop a vision for 2050. And so the cogeneration sector is committed to a resilient, decentralized and carbon neutral European energy system where cogeneration can play an important role. This is an overview of CHP today. So the CHP installed capacity has been stable over the past 5 to 10 years, but the CHP fuel mix has been changing quite a lot in the last 10 years. This is based on the latest Eurostat data showing that indeed the CHP mix is becoming less carbon intensive, with coal being phased out, and renewables being phased in. In fact, the share of renewables has almost doubled in the last 10 years, from growing from 13% in 2009 to 25% in 2019. And most of this renewable energy in the CHP mix is actually represented by biomass. So we see that there's still quite some potential for biomass to grow, and it goes in tandem with the phase out of coal, I would say, from a CHP perspective. So what are the benefits of CHP? First of all, energy efficiency. With CHP, you are able to provide higher value when using the same fuel to generate simultaneously heat and electricity. And as I've just mentioned, biomass and bioenergy in general is one of the energy sources that can be used with CHP. And we all know that these are very valuable resources. So we always advocate for CHP to be prioritized whenever thermal fuel is used. Then we also see that CHP has increasing value from a systems perspective and from a flexibility perspective beyond energy efficiency. And you can see here that we're increasingly seeing CHP as a way to integrate energy systems, so heat, electricity, gas networks, but also bioenergy as an energy source, and also integrating the agricultural sector when it comes to biomass and biogases, and so on. And then there's also the flexibility angle, and this picture comes from our 2050 study, where we have modeled the entire energy system, and we've optimized, or the consultants have optimized the use of CHP to actually complement intermittent renewables and increasing shares of electrification. This actually shows Germany in 2050 in a net zero energy system, where you can clearly see the differences in energy demand between winter and summer. So in winter, we will by then have electrified quite a lot of heat, and then electricity demand will be quite high in winter compared to summer. And then you see that CHP can play quite an important role in supplying residual demand, even at times of very high wind and solar supply, but especially at times of insufficient supply of intermittent renewables. And some of that CHP will be running on biomass. So what is the biomass potential looking forward? And here I've taken the Commission's 1.5 tech scenario for 2050. So in 2050, we see that there's quite a lot of system electrification, either through direct electrification of demand or through indirect electrification. So we're seeing more and more discussion around hydrogen. So what will happen is that the power capacity will increase significantly in response to these trends. And then what will also happen is that demand will be decreasing. So there's, at least in the 1.5 tech scenario, there's quite ambitious assumptions around demand reductions. But even if we reduce demand significantly, and even if we increase electrification significantly, there will still be a need for thermal energy. So here you can see the conclusion that thermal energy use is reduced, but is still necessary for system resiliency and a cost-effective decarbonization of the energy system. And here you can see that the biomass overall will actually increase its share in final energy consumption, and it also in absolute terms it will stay stable or even increase. So really there's a need for biomass, and then when that biomass will need to be used, then CHP will be the most efficient way of using this fuel. And here again, this comes from our 2050 study carried out by Artelis. So they've actually looked at the various applications and sectors. So you can see final energy demand for space heating in buildings and final energy demand for industrial heat. And there as well, you can see that biomass will play an important role in both industry and buildings and the building sector. And there is an opportunity for CHP to be optimized to deliver not only energy efficiency, but also ensure that higher flexibility, or the energy system benefits from higher flexibility. There's also the synergy between CHP and electrification, because of course you need electricity, at the same time you need heat in winter. And I think that will play an important role increasingly. So what about the Renewables Directive? We are following Fit for 55, and the Renewables RED 3 is one of our priority files. We see that it plays an important role in delivering Fit for 55 objectives as well. So we have the -55% greenhouse gas target, which really requires a more ambitious uptake of renewable energy. So the Commission has increased the renewables target as well. So the Commission also points out that with the focus on system integration and hydrogen strategies, there needs to be higher focus on energy efficiency, on renewables complementing electrification, as well as renewable fuels. And yeah, these are additional elements that link to the Renewable Energy Directive revision. So promoting energy efficiency and renewables in buildings. Also, there's a focus on intermittent renewables like wind, and higher level of biodiversity protection. You can see here an overview also from the Commission in terms of the sub-targets that will be contributing to the 40% proposed target for renewables. And there is definitely a focus on increasing renewable shares in buildings. So there's now an indicative target for renewables in buildings of 49%. There's also a focus on district heating and increasing the share of renewables in district heating while expanding district heating. And also renewable energy in heating and cooling. That's also part of the toolbox of boosting renewable energy uptake. On the other hand, we have bioenergy criteria being revised again. I will leave this to Bioenergy Europe. We are concerned about actually stability of the framework. So if the rules change every 2 years, then investments cannot be done in a predictable way. So from our perspective, it's good to make sure that bioenergy is sourced in a sustainable way, that we focus on the efficiency of bioenergy use, but then changing the rules all the time will not ensure a stable environment for investments. So what will be the impact on CHP of the Renewables Directive? We see that RED 3 features a focus on energy efficiency first. So this will favor CHP. Then on biomass specifically, we do like the fact that CHP is preferred to power-only plants. But then, as I've just mentioned, having too strict requirements will limit the availability of biomass, biogas, biomethane for CHP operation. There's also a focus on hydrogen and renewable gases, which is out of the scope of our discussion today, but that's still important for CHP. We also see waste heat is an important point. District heating as well. We think it's a good development for CHP as long as CHP is recognized as a way to as a heat source for CHP. Then the focus on buildings is welcome. Many of the buildings will be electrified, but a large proportion of buildings and businesses cannot be cost effectively electrified, and that's an opportunity for CHP. And then, as I mentioned, heating and cooling as well is in the focus, and it needs to be in the focus because it's a big challenge to decarbonize the sector. So here are high-level policy asks for the Renewables Directive. We support the efficient switch to renewable energy in electricity, heat, and gas. We promote efficient district heating uptake for an increasingly renewable energy system. We promote local energy system integration to maximize renewable energy use. So that's where CHP and especially biomass CHP can play a role, because it not only increases energy efficiency, but it increases the flexibility of the energy system as a whole, and it also contributes to higher shares of renewables in both electricity and heat. We are also asking, we do accept that electrification will happen, but this needs to be carried out in an efficient and increasingly renewable way. We should not electrify sectors where there's not enough renewables to electrify. And also we advocate for a robust, ambitious, and predictable framework for renewable energy. And this applies especially for biomass sustainability criteria. And then our biggest ask and our call to action is that we need an ambitious and predictable regulatory framework to be set in place to reap the benefits of cogeneration now towards 2030 and towards 2050. And that's why we ask for cogeneration to be prioritized for all thermally generated heat and power in an attempt to maximize the use of valuable energy resources. That's all from my side, and I'm happy to answer any questions as part of the discussion. Thank you.
Thank you so much, Alexandra. That was a very interesting and to the point presentation. So I will remind to the audience that they can use the Q&A box down below, not the chat box. And then we will pick the questions and we will answer them at the end of the presentation. So I will kindly ask Michał Długosz from Bioenergy Europe to take the floor. Hi, Michał.
Hello, hi. Hello, Giulio.
Michał will give us a presentation focusing on the role of bioenergy more in general, but of course also mentioning the...
First of all, thank you, Alexandra, for very good presentation. A lot of important points for us, like system integration, stability of the system, flexibility, energy and resource efficiency, GHG savings. So these points we fully are in line in this regard. In my presentation, I would like to shortly introduce more data on bioenergy, and on top of it also focus on the mentioned by you also revision of Renewable Energy Directive. Very briefly, Bioenergy Europe, we're a trade association established in 1990 in Brussels. We gather around 180 companies, 180 members, 130 companies, 30 associations, and around 20 different type of research and academia. And basic information about bioenergy. So when we discuss energy transition, we usually, in this discussion, we have usually reference to solar and wind as the main driver of decarbonization. It is true for the power sector, but we should understand that energy system is much more than a power sector. So overall, bioenergy provides around 10% of gross final energy consumption in the EU, which can be translated into almost 60% of all renewables. And the special, let's say, feature of bioenergy is that this is versatile resource used in heating and electricity and in transport sectors. In this graph, we can see that biomass provides a crucial contribution almost to all member states, considering their, let's say, share of renewable energy resources. So at the EU level, this value of bioenergy contribution is around 60%, with countries which reach several countries where this number is even higher. So biomass provides crucial contribution for meeting renewable energy targets. And when we discuss heating, as was also pointed out by Alexandra, biomass is one of the key drivers of decarbonization of heating sector. Currently, within the heating sector, it provides 16.7% of contribution to energy use in the heating sector. Slide. When we discuss the future of bioenergy, we rather have like this a bit like schizophrenic, I would say, schizophrenic approach, because on the one hand we are often in a spotlight where biomass is targeted as this resource which is not green enough and which poses a significant challenges to environmental outlook of the EU. On the other hand, based on the projections of the European Commission, we can see that the growth of bioenergy sector will be stable and will even increase. So these are the scenarios within communication on the climate target plan, and within each of these scenarios, both in until 2030 and further until 2050, the share of sustainable biomass will grow. This is the assessment of both impact assessment of mentioned communication, but also what is I think very important for us, national energy and climate plans, which are let's say the assessment of member states itself, how they perceive the evolution of their energy mix and systems in the future. And as you can see on the right hand side, we can see, I would say, moderate or maybe even more significant growth for heat and electricity, which are both around between 25 and 30%, and very strong growth in transport sector. So overall, based on these projections, we can see that share of biomass will be growing steadily in the EU. And now let's talk about regulations. Indeed, the stable and I would say permissive, supportive regulatory framework is key for the sector. Alexandra also mentioned that for the investment certainty, it is necessary that rules will be clear and will be fair. So due to time constraint, as we know that Fit for 55 package is a very comprehensive and very broad piece of, let's say, there are 12 pieces of legislation referring to, let's say, each sector of the energy system functioning. I would like to focus only on the Renewable Energy Directive. For us, Renewable Energy Directive is a key legal act, not only because it provides the general framework for renewable energy development, but also more precisely because it sets so-called sustainability criteria. So sustainability criteria are these criteria which guarantee, if met, that the biomass is sustainable. And as sustainable, it is accounted to the renewable energy share. Its emission rating is 0 within the EU ETS, which is one of the crucial competitiveness drivers of biomass solutions in the EU, and also that it is eligible for public support. So just to brief you, in the current Renewable Energy Directive, which was adopted in 2018, the deadline for the transposition of sustainability criteria was 2021. Then it would have its, let's say, and in 2023, based on the functioning of the system, we should have the first prospective revision of sustainability criteria. So this was the first cycle. Unfortunately, it has been already broken. So the RED III directive sets completely new framework. Before, actually, member states were able to transpose the existing sustainability criteria. So based on our assessment, out of EU 27, within the deadline, which was July 2021, only 3 member states were able to transpose sustainability criteria to their legislation. We can say that this is the fault of member states, but on the other hand, the Commission also is pending with several key legal acts crucial for this transposition, which is delegated acts on the compliance of forest biomass with sustainability criteria, guidance document, and also on the voluntary certification schemes. Nevertheless, what is so basically the situation there is quite chaotic, and on the top of this, let's say, flags, we are like, we'll receive new regulatory framework governing biomass. And now I will just go through the main elements of the revision of sustainability criteria. One of them is a question of threshold, which installation need to prove or need to undergo certification. So first, in the current directive, we had a 20 megawatts threshold, which was in line with the EU ETS 20 megawatts threshold. In RED III proposal, we have a drop to 5 megawatts, which includes very small installations. For us, this change is unacceptable. We think that in this regard, the number of entities will grow significantly, while the volume of certified biomass will not grow significantly. 20 megawatts encompass around 15% of biomass users and around 75% of biomass used. So we think this solution is efficient and does not pose additional administrative burden on many entities. Another question, which I think is crucial for the investment safety and certainty of the framework, is a question of GHG emission savings. So in the current legislation, 80% GHG emission savings should meet only this installation, which will start operating from January 26. In the revised RED III, all biomass installations should reach 80% GHG savings from 26 onwards, which is, I would say, it may be a big challenge for installations which are already being, for example, built and were designed to meet different GHG savings potential. Another question, which maybe is not really very close to the main objects and subject of this seminar, is a question of forestry. We have, I would say, incremental attempts of the European Commission to regulate forest practices via RED III. In this regard, it refers, for example, for high biodiversity forests, and the question of setting definitions at the EU level. In general, we support higher transparency, we support higher sustainability standards, but in this process, we should also remember that definitions set at the EU level should be flexible enough to encompass different practices in member states. This is also most related to forestry, and this is also, let's say, concerning technicalities on the cascading use of wood, which means that the highest quality wood should be used for, let's say, more quality-based industry related to wood, while biomass mostly refers to it's based on the residues. Another topic, which maybe in case of cogeneration is a good news, is a question of the support for electricity only power plants. So RED III sets deadline of 2027 for the support of a production of electricity from forest biomass in electricity only installations with few exemptions. We also think that this is premature. This framework should be, this support should be set at least 2030 to incentivize reaching targets for 2030. So thank you for your attention. I think I'm above my 10 minutes. Nevertheless, I would like to underline one key point. It is regulatory stability and certainty. And with revision of sustainability criteria, when in general we support the direction, the direction towards higher sustainability, higher transparency is a good direction. The question is to do it in a I would say responsible way, not to thwart sector in meantime, and to allow member states to transpose sustainability criteria, to develop own national rules, setting, for example, certification standards, and to avoid the situation which we have right now, which can be described by one word, chaos. So thank you. This is from my side, and sorry for these problems with the screen. As I mentioned, I work on two screens and I didn't foresee it. Very sorry for this.
No worries. Thank you, Michał, and thank you for the very nice presentation. And yeah, no worries. Thank you, Michał, and thank you for the very nice presentation. And yes, I will agree that policy stability and stable frameworks that do not change every 2 or 3 years are very, very important. So we will go into the let's say second section of this webinar, where we'll have the presentation from the two projects I mentioned before. So we'll see real implementations of Biomass CHP. So I will call first Nicola Rovelli from Enereco. Enereco works on the Blaze project, the project which also EUBIA is involved in, and he will give us some details on the actual work carried on the field.
Good morning,
Nicola, the floor is yours.
Thank you very much. And thank you also to the previous panelists, that it was very interesting. So I will give you a brief introduction of Blaze project. I'm Nicola Rovelli. I'm the head of the R&D and Innovation Department of Enereco. Enereco is an engineering company working mainly on the oil and gas industries, say in Italy, in Europe, and also abroad. But we started some years ago diversification roadmap, and we joined the Blaze project this year. So what is Blaze? So today I'm going to show to describe briefly the Blaze project, and let's say, since Enereco is responsible not only for the system integration of the gasification unit, so an engineering part, but is also responsible for the together with the EUBIA or the market analysis and the business model, business case especially. I think that this is the right webinar with the right person to start talking, because this activity has been started just few weeks ago. So just go through. I will just focus attention on the Blaze project, the concept of the CHP that is specific for this kind of technology, and then they expect the application and Blaze objective, and then I will describe you the biomass potential selection, because to start with this project we have we had to select a certain kind of biomass. And then we started I will give you just the first results or conclusion that is just starting point from the for the market analysis and the business case, business model. So the project is a biomass, low-cost, advanced, zero-emission, small to medium-scale integrated gasify and fuel cell CHP plant. Actually, is an European project funded under the Horizon 2020 program. It involves industries like Enereco, EUBIA, Walter Tosto, Solid Power, and also associations like EUBIA, ETA Florence, and also some of the main university like Università dell'Aquila, University of Guglielmo Marconi, that is leading the coordinating the project, Università of Teramo, EPFL, INEA, that is a research center. So that's more or less the partners that are on this project. We have the project is completed by 9 work packages. It was a 3 years project, but we had to extend to several, not only COVID but also other reasons. Was financed at 4.3 million, and as I mentioned, we have 10 partners. So how Blaze project is composed? So basically, we get to this CHP cogeneration system by combining, integrating 2 specific and let me say promising technologies. One is the gasification, and one is the solid oxide fuel cell. The gasification is an old technology, but the innovative one that is applied here is a dual bubbling fluidized bed technology that is very specific and came out this kind of technology from several previous projects financed again under national and European projects. And the characteristic of the gasification, of course, is that we release actually a syngas from, let's say, from the gasification of the biomass. We have a syngas that is rich in hydrogen and carbon monoxide, but not only. The point is that also the syngas is very hot, and then we integrate this with a solid oxide fuel cell that is very promising as a technology. And is under development this moment, and the other point is that this fuel cell works at high temperature, so we can send directly, let me say directly, the syngas to the fuel cell at high temperature. The point is that where the issue here is that the fuel cell is very, since it's solid oxide fuel cell, is very strict in terms of grade of syngas that can be accepted, because the small pollutant of chlorine or sulfur may poison the fuel cell and ruin forever. The system is integrated, so we have practically we have a section of between the gasifier and the fuel cell where we have a hot gas cleaning unit system. And we have also a system for recovering the heat from one process to the other in order to optimize the system. So basically, it's this one. I not go too much in detail because maybe not too much. I want to details on something that you can find on our website of the project. But what we today I will focus the point is that on the biomass. So we identified some biomass that can be suitable for our system, and so we selected, let's say, 7 categories that are primary residues from forest, agricultural residues, secondary residues from wood industry, and also industry using agricultural products like agri-food, municipal organic waste, waste from wood, and digestate. So we just checked all these 7 categories in order to identify which one is the most providing, but not only, also in which kind of biomass inside those categories are suitable for this unit. I not go through the technical details, but this is just representing how complex became the plant due to the fact that we have a gasification system on the on the bottom part, that is where the biomass is gasified, and then we have some catalytic candles for removing the ashes, and then also we have the first let's say tar reformer. Then we have also other reactors to again remove the tar and also remove the chlorine and the sulfur before going into the fuel cell unit, and then also all the streams related to duties related to this. So as you can see, the plant became quite complicated during the project development. So which was the objective of Blaze? Just to give you the focus of where we started. So the idea is to have a CHP, to develop a CHP that could take from the small CHP capacity to the medium CHP capacity, between 2500 kilowatt electric, and then from, let's say, 0.55 megawatt. The expected, the objective that was written in the proposal was to achieve 90% of the overall efficiency and an electrical efficiency of 50% in respect of what is the current CHP typical efficiency, that are 65 and 25% electrical. Actually, again, these are some results that we are developing in this moment. At the moment, we have an electrical efficiency that reached 48%, and also the overall efficiency a little bit lower than 90%. But again, it's still above the let me say, the standard value that we know. The investment cost that we let's say we supposed to go in a very cheap point, let's say going to 40,000 euro for kilowatt electric, but as well as the operating cost. But due to several reasons, the cost is increasing a lot, since for several reasons that then I will explain you later. Okay, then one of the first activity that we carried out was to select and characterize the biomass. So how we started, just very simple. We just tried to analyze the data regarding the biomass availability, and we tried to with the toolbox that is under the S2 Biome project. And so we selected the total biomass potential availability. That is quite interesting as a value. Then for each category, we go through and define the biomass type. And these, let's say, for example, the agricultural residues, we also look to what is inside, like residue from fruit tree, olive trees, plantation, citrus tree. From this point of view, then, and this was done for the world category, and then we get also to the point to identify the location of where this biomass is available. So in order to also have a starting point to also think about some business cases specifically. The second part was also to understand that this was a first exercise that we carried out just to have an idea of the potential of CHP. Of course, it's just a numeric calculation that is not probably too much realistic, but again, considering the projection of the European record on the potential of bioenergy CHP in EU27, that is, let's say, not one of the. I know that there is a new updated version of this document. When this the deliverable was carried out, we had this value. But anyway, these things are promising, and also we thought to, I mean, think about, okay, what if the Blaze concept can just replace 100% of the CHP that are available. Of course, is probably not realistic number, but even if we get to 10% of replacing or having the space on the CHP system, still the number are promising. So just imagine, just look to we make some very preliminary number of plants that can be installed. Just considering 100% replacement, but if you just divide by 10, you have 10% of the replacement. So even if we go to 10% of replacement of existing CHP, we go to a 1,400 number of unit of 5 MW. That still is interesting for the industry. So starting with this, we go through and we tried to analyze which are the biomass that should be used, that could be used in our system. Of course, we had to select 10 sample and 5 mixture in order to see the real feasibility of using this gasification unit for those biomass. So the biomass that has been selected considering basically three criteria. The first one is, as I mentioned before, was the biomass availability. Then the biomass repartition per typology and in terms of energy available. So also this parameter was, and also the biomass cost. So we had to, again, talking about what has been said just a few minutes before, we have to look to the sustainability of the system. So we have to go where this biomass is available and not used and have a poor value. So those are the biomass that's been used, that have been tested, and these are the results. So all what the first analysis of biomass availability and also this characterization is already available in our deliverable 2.1 that is available in our project website. And just to show you what was the came out, considering just to give you a very big high level idea of gasification. Gasification have some issues related to humidity of the biomass. So the biomass is preferable to be dried as much as possible. So, for example, wood chips would be a perfect kind of biomass to be used. The second point is the ash content, because we should also try to find the right biomass that also cause less secondary waste from the process. And also have at lowest point value of content of sulfur and chlorine, because this kind of contaminants could poison, as I said, the fuel oxide fuel cell. And one of the other parameters, this technological parameter, is also the ash melting point. So we have to find that the ashes that should not have a temperature below, let's say, 900 degrees Celsius, that is the operating temperature of the gasifier. Otherwise, it will be clogged the system. So considering this, let's say, apart 2, 3 that they have this problem of ash melting point, all the rest should be, are manageable. Of course, it will increase the cost. If I have not a dry biomass, I have to increase the cost of the biomass. The cost of the system to make it dry, so some heat recovery that cannot be used then for the cogeneration. And also, if I have high content of sulfur and chloride, is again doable, but probably will increase a little bit the cost of the system. So going to the, as I mentioned, just to summarize the conclusion regarding the biomass characterization, the study was carried out availability from the USGM, Università Guglielmo Marconi, and the ENEA, Italian Research Center, carried out all the tests regarding all the biomass that was selected. And with exception of few biomass like corn cobs, black lime, or digestate, all the feedstock can be used on the unit by using some additional device or operating correctly the unit. And the other point is that we have to be aware of the risk of poisoning of the fuel cell. This means that this kind of technology is promising, since is quite flexible, the kind of biomass input. So I got to the conclusion. So this is my last slide. That is where we are at the moment. As I mentioned, we selected the gasifier. Another point that we didn't, I didn't mention that to now, we almost complete the design of the unit. We define all the things that should be required. So, which are the current outcome? For sure, the system is increased in complexity since we had to add some additional unit for gas cleaning and also for gas pressurizing, for example, with the steam blower. And also we have the other point is that at the moment we have a lot of uncertainties related to the final commercial cost of the solid oxide fuel cell. This, as I mentioned, is under development. And then also the other issue, what I didn't mention is that we have a pilot in Valtertosto premises that is 100 kilowatt thermal, and that could go to a 50 kilowatt electric, but we have just a solid oxide fuel cell for 25 kilowatt electric. So half of the potential power of the singles is not used, but means that we already have a pilot related to a small scale gasifier. What we discovered is that all this complication of this unit, and also to the fact that we don't have for such small kind of unit commercial equipment, for example, a blower at high temperature, this is increasing the capex and the opex for sure for the small scale. What we believe is that for the commercial, probably for the medium scale, probably these can be, managed, the additional cost, since we will find, probably we can find on the market some commercial unit that are not available for such kind of small unit. Moreover, the plant is quite, let me say, complex also from an operating point of view. So we need still to develop some additional control system, to be correctly handled, and probably all this should be probably is better to have a plant of probably between 0.5 and 5 megawatt electric as an outcome. And this means that we will go probably in the small and medium industries or large public commercial areas or district heating. So this kind of plant probably is more suitable for this kind of things, so that could replace, for example, some small incinerators. So that's more or less the conclusion that we have developed so far. We will still work on the market analysis, and also I thank my previous colleagues that talk here, because for us it's a very big input for the development of the business case. So thank you, everybody. I'm available for any clarification.
Thank you, Nicola. There are actually two questions. Maybe since they're kind of more technical, we could try to answer them now. Christopher Marches asks if you plan to include biomass from forest planted for biomass production in the Blaze plant. As I'm also part of the Blaze project, I would reply that the Blaze plant was planned to use residues, and this the forest plant for biomass production were not originally included for that. Do you have something to add?
Yes, because this is also is going back to the point of general terms of sustainability.
Yeah,
we need to go not to have a specific plant or cultivation for having the biomass like we had in Italy for the biogas. We need, in my opinion, we need to recover as much as possible all the residues that are not valorized. And this is my personal opinion, but I agree with you that also the Blaze was focused on the residues.
Okay, so we can go to the next speaker. Thank you, Nicola. We have Athanase Vafeas from Dowel Innovation, partners of the SmartCHP project. Athanase, the floor is yours.
So many thanks to all of you. So I am. Can you see my screen first? I will.
Yes. Nicola, can you switch off the camera and the micro? Yes. Okay, great. Okay.
Can you see it in the correct mode?
Yes.
Okay, excellent. So I am Athanase Vafeas from Dowel Innovation. The Dowel Innovation is an innovation consultant company. So in various forms, it exists since 1985. So working in energy transition at large. Here we are supporting the project on the value form, on the techno-economical analysis, and also on the exploitation. So Smart CHP is about small-scale cogeneration in order to produce some renewable heat and electricity from biomass. My talk plan will be a focus. I will start with the Smart CHP project in brief, then a few elements from the first year regarding an assessment of the market potential of the unit, then something which is quite recent. This is why there is a small disclaimer. The deliverable was just submitted this week, so it's quite recent regarding preliminary calculation on the use case and some conclusions and next step. So the focus will be more on the value side. There are some technical work package and as well some work package dealing with biomass selections that have been run and still ongoing in parallel. But my topic is today on the focus on techno-economic things. So in a nutshell, in brief, Smart CHP is about, so it's a EU research project, EU-funded research project coordinated by BTG with 10 partners over 6 countries. So it's a 4.5 year in terms of duration. There was a 6 months extension due to the COVID, 4 million euro. So it includes universities, as you can see, companies, and industrial companies, and innovation experts. So it's about combining cogeneration and renewable. The aim of the project is to design, to develop a highly flexible, a small-scale CHP system based on a modified engine that you can see in the picture. The size, the tentative size, the range is 100 to 1,000 kilowatt in terms of electricity, meaning it's a mini cogeneration system. It is fueled with fast pyrolysis bio-oil. So you can see on the left the value chain starting from the fields, the non-food biomass, to the yellow circle with the pyrolysis oil, the bio-oil, which is obtained in order to feed the blue circle, which is the Smart CHP engines. So this is based on various non-food biomass, including, for example, like lignocellulosic wastes and other residues from agriculture or organic elements as it is. The full value chain is here in the pictures from left to the sides. So on the left, you have the inputs. The focus of the project is the blue center, which is the modified diesel engine complemented with the flue gas boiler, taking profit of the generated heat. So this is the cogeneration system, plus some flexible ability thanks to a smart control unit that may change dynamically the heat to electricity ratio in order to produce applications in terms of electricity, heat, and cooling in a flexible mode for application in industry, in commercial, district heating, and other remote non-connected areas. Key features regarding the Smart CHP. So we are in the class of 0.1 to 1 megawatt electric. The first big value is the high flexibility of the heat to power ratio. A second value is the integration with other renewable, including photovoltaic mainly. The standardized fuel characteristic in the input fuel, in the bio-oil, the possibility to retrofit all low efficiency systems, the ease of use and ergonomy, and some reduction ambitions in greenhouse as claimed by the RED 2 and the future RED 3 directive. Regarding Smart CHP KPIs, here are some tentative and the contractual technical and economic objectives we claim to reach with an overall efficiency at 85%. Here, an electric efficiency above 40%. So you will see in our calculations, we were more conservative using a 32 electric efficiency, to start with something conservative, and some economic objectives that are set here with 1.2 kilo euro per kilowatt in terms of capex, and some 15 cents for the OPEX. So a quick overview of the year one regarding the value, the market assessments. So initial market assessments are close to the one that we investigate through classical cogeneration, including hospital, hotels, office building, educational buildings. So one market segment of particular interest, especially for the Netherlands, with many partners in this country, are greenhouse. So we put in the short list as well. So we have here two cases taken from the Code 2 Observatory as an illustration, but let's move forward. So a structural setting was the positioning of the pyrolysis infrastructure, the pyrolysis unit. So to do that, we had to combine the market assessment and the availability of the feedstock potential and availability on a local dimension, including the quality of the biomass and the characterization. Another dimension which is important is the energy price at the local level, since this has a direct impact in terms of the economics of the system, enabling context in terms of environment, geographical spread. So this enables us to select some countries in terms of high potential. So we selected Greece, Romania, Croatia. So Netherlands and Sweden connected with an import scenario. So Sweden for the pyrolysis plant, serving internal purposes in terms of energy, plus an export or import with respect to Netherlands. And this is also connected with the availability of the biomass. So for example, for Greece in Southern Europe, we selected the olive biomass based on the olive kernel. In Romania, corn stover, etc. For Sweden, softwood residues from forest. So next, the last year deliverable on the market assessments made with Exergia, which is public. You can find it on the internet, on the website of the project, starting with these 5 countries. And going to the market analysis in terms of potential. So here we have the 6 market segments I mentioned just before. We make a market assessment coming to unit counting the based on specific energy consumption. Sorry, specific energy consumptions for hotels that can be said per square meter, or for hospital per bed. We can and based on Eurostat available information, we calculated for each of the market segment and for each of the country the potential in terms of number of units, which are publicly explained in the deliverable 6.1. So this combined with the places where we position the green elements, Misca-Cantus, Sisak, so Croatia. In Greece, it is in Crete, the selected site for collecting olive biomass in the region. In Sweden, it's an import scenario. Romania, a city close to Bucharest, Slobozia, and the location for Sweden was Boras in the western part, close to Göteborg. And these are the amounts. So next, in the next steps, I will introduce the first case in brief, which is the hospital in Crete. In Greece, in Crete Island, in Greece, with some limited potential in terms of number, but the idea was to launch a process and the methodology for the profitability analysis. So to do that, you will see we need data. So it was difficult to find actual data, so I will explain the process we have used in order to build some proxies when the data were missing. So the general framework in terms of analysis, as I mentioned on the very beginning, we have these 4 stages, starting with the field, with the biomass economics, then the pyrolysis economics, then the smart CHP economics, and then the energy use economics. So in the work package 6, which is the work package we are leading on the techno-economic analysis, we will focus on the step 3 and step 4 for the use case. So we are energy user centric, and of course we will use economics coming from the pyrolysis process or the biomass process, including as an input the price or the cost of the 1 liter of bio oil. So this is an input data for us, and the focus will be more here in my next slides regarding the time series and the energy needs. So let's speak about the case. So the case is the hospital is closed in Heraklion. Perhaps you have visited Crete Island in some holidays and vacations. The pyrolysis plant is in the agricultural region of Crete, in the south center of Crete, which is the land of Messara, with a lot of olive production, for example. And the idea and the distance between the green pyrolysis plant and the hospital case in Heraklion is about 50 kilometers. The hospital is quite old with low efficiency systems. It's about 400 beds with 1,000 employees. So it's quite big for Crete. And we selected the case beyond the potential of the island due to the fact that we found an article that reported some actual energy needs and actual energy bills. So this was quite determinant for the selection because, as I said, the lack of data might impact the elements. So the annual consumptions in terms of electricity needs and thermal needs are these levels. So you can see that the heat to electricity ratio is 0.5. It's quite below 1. So it's a little bit curious, but the idea is to launch the process. So what was missing in the analysis or in the reported case was the seasonal variation, the seasonal breakdown of this annual electricity needs that were actual. So we use a flat assumptions for electricity, considering that it is an hospital with a constant and a steady operation all along the year. But we use some limited seasonal variation in order to allocate the thermal needs according to the 4 seasons. So you can see some variations in summer and spring. So the first step we made was to assess the profitability of a simple cogeneration system, an annual simulation with no activation of the flexibility components, the one that control the heat booster when additional heat is needed. So the assumptions we have used are the following. So we selected the 500 kilowatt electricity system, which is fed by pyrolysis oil. So we designed it based on the base heat, an operation mode at 5,000 hours with 70% of capacity factor. So this was the recommendation of the designer and the manufacturer of the system. The unit cost of the bio oil at 0.35 euro per liter, and some fixed efficiencies, electric at 32 and heat efficiency at 53. So based on that, and of course we have used in order to value the energy, the actual contractual price of the energy price of the hospital. As a reminder, it was with oil price for the heating needs of the hospital, which is not the best solution. So under this assumption and the data, we have a first calculation at 37. So it's positive, so which is quite promising. But of course, this is a very rough calculation, not taking into account some imbalances. So sometimes there might be electricity in excess, so heat in excess, meaning heat flaring, which is not very efficient, and all the energy in excess. So in order to do that, we need to adapt and to go to hourly simulation on typical days according to the winter, and to enter to the hourly scale, to the granularity scales, we need some assumptions because the actual data were missing. So what was the process in order to elaborate the volume? This is quite easy because from the seasonal variation and the seasonal amounts that were here, so here for the thermal needs, we just divided per season by the 91 days, and we elaborated the amount for a typical winter day in terms of thermal needs, same thing for the summer day. We did the same for electricity. From the seasonal breakdown of the demand. So here we can see it's a flat profile, winter equals summer. So meaning that the electricity, the daily amount of electricity is this amount. So this has the volume has to be combined now with load patterns. So the load patterns we created these profiles of the typical days for electricity and thermal needs based on literature review and from older projects we took part. So for electricity, we can see here that the electricity profile is low at night with a peak on the morning. We call it flat night, priority morning as a typical profile. And the integral, which is below the curves, the orange curves, is exactly the 13.4 daily amount, which is here. So same for the thermal daily consumption. You can see it's more complex because based on the literature we use for hospital, the profile that was provided by the project that we use focus on one peak in summer and two peaks in winter that are displayed in the graphic in terms of demand. So when we combine all these elements with the operation, as we had as an instruction from the designer to work, the machine has to work at 70% capacity factor during 5,000 hours. So it's a starting assumptions. We'll play a little bit with the number of hours. We'll see that in order to improve the results. So, but of course, the 5,000 hours can be allocated in various modes all along the years. So we selected two modes. The first one is we consider the machine is flat, is operated in a flat mode with no daily variation, with the fixed efficiency, and giving the priority to summer. So it's an assumption here. So meaning that summer day 91, so autumn is like summer, so 91 days, and some days in spring, and this is the total to reach the 5,000 hours. But there might be a second operation mode, and we want to compare these two operation modes, the modes which is working only the day on, night off. So you can see the profile on the right, and you can see here on the middle, the winter, spring, summer, autumn breakdown is there is no seasonal preference except the maintenance off during summer, during 30 days, during 1 month. So you can see that the number of the 5,000 hours are the same with respect to the two operation modes. So let's go to the results quickly on the operation mode 1. So we made the calculation and we go quick on the electricity balance, on the thermal energy balance, distinguishing the winter day and the summer days. And you can see in some situation, the balance is positive, meaning that there is some heat in excess, which is not an undesired solution. It's not very efficient, and there is some heat flaring for thermal in these operation modes. So this is not very good, and you will see that in terms of results. So when we valorize the energy which is produced at the price of the contractual price of electricity and heat as contracted by the hospital and the input price of the bio oil, we have a negative result. So which, of course, it was expected since there is some heat flaring during due to the wrong operation that was opted. So we need to increase the 5,000 hours. We can play with it, and we add 1 month of operation, and we reach almost the balance. So it's the negative balance is offset with adding one month of operation. But as you can see, it's not very positive. So we need to go to the second operation, and you will see that it's more favorable here. Same process, electricity balance, thermal energy balance. So there is it matched better. You can see that this match better to the demand profile. So we can expect a better improved results, which is the case here with a positive estimation when you integrate the three profiles, the 3 typical days over the year. So meaning that the 15 hours of operation a day is much more profitable according to the simulated and the proxy used for the energy demands. So meaning that the mode of operation matters. But it's not the only parameter that matters. Of course, the mode of operation matters. So my conclusion is the following. There are a series of parameters that have a direct impact in the profitability. Of course, the cost of bio oil, all the non-bio oil expenditures, including the maintenance, the depreciation, which depends on the capex of the system, and all the other ancillary fuels that can be used like ethanol in order to smooth the technical part of the machine. Contractual cost of energy, so here the price of oil and the price of electricity has a direct impact in terms of profitability. There are some other parameters that are not in the simulation yet, possible incentives or the possibility to sell back the excess of electricity. So for the next steps, what is needed now, we need to multiply the cases, especially to go to some specific cases with heat to electricity ratio higher than 1 and with flexible elements. Here, of course, there is a decoupling of electricity demand and heat demand, which can be also the case of the next cases. So we need to elaborate and select cases in order to take the best profit of a flexible operation and the flexible operation of the smart CHP in order to adapt to a wide spectrum of heat to electricity demand. So one critical point is the lack of actual consumption data. So if some of you have some cases with documented data and that you are willing to see your case in the simulation, if it is compliant with the country we have just presented, so feel free to contact us for that. Just the final image is the model of the flexible operation, playing with the ratio and the control system in a dynamic mode in order to distribute the input fuel, the pyrolysis oil fuel, to the CHP, the diesel engine, or to the boiler with a dynamic ratio in order to serve to electricity and to type of heat as an extra booster. This is particularly relevant in order to compensate fluctuation when you have a hybrid system, including, for example, photovoltaic generation and with additional electricity and need for heat that will be critical at that time. So many thanks for your attention. I think I'm through, yes. And should you have any question, I will be pleased to answer.
Thank you, Athanase, for the presentations. So again, I encourage those who have questions to use the Q&A section down below. We have answered some of the previous questions, either speaking or either by typing. In the meantime, I will perhaps start, since we have like 15 minutes left. We'll start the last round, so let's say the feedback round. So I will ask Michał and Alexandra if they have comments on these two last presentations, if let's say the trends that they have depicted in their presentations are somehow reflected in these projects that we have seen now. I mean, if the applications, the type of feedstock or the market uptake pathways. If you have comments on that, if you see that these are the applications that we will see in the next 10, 20, 30 years, or if there are also other things to improve, other applications to consider.
Yeah, maybe I could start.
Yeah, go on.
So I would like to put this discussion in the broader context of energy trends that we see today. We know we must rapidly decarbonize our energy sector. The building sector and the commercial sector are very important because they're hard to decarbonize. We only hear about industry and transport being hard to decarbonize, but actually heating and cooling and buildings are hard to decarbonize in their own way. So I think that's one thing that needs to be taken into account, that we need all renewable energy solutions and energy efficiency solutions in the building sector and in the small commercial sector. And then we also see the whole debate on energy prices. That's something that must be taken into account if we want to decarbonize, if we want the energy system to remain resilient and flexible and secure, and if we don't want blackouts every other day. I think we need to diversify the energy sources that we're going to rely on. And that will also ensure not only energy security, but also the cost effectiveness for consumers. So restricting any solutions that will provide decarbonization will automatically increase the overall energy cost of the system, and then eventually consumers will suffer because they will be hit by very high energy prices. So that's another element to be taken into account. And of course, we must not forget about the local aspect. So there may be areas where there's no problem in electrifying most of heating and cooling demand, but perhaps there are other areas where electricity grids are not so well developed, where we would need to invest a lot in new infrastructure, and where feedstock and energy sources like biomass, biogases would be the best way to decarbonize certain sectors. So I think that's really it's important to contextualize, and it's important to move away from the technicalities as well and see the bigger picture, but also look at the local aspects as well. So
Yeah, thank you.
That's it from my side at this stage.
Yeah, absolutely. The point that we cannot, in the short, at least in the short medium term, it's unthinkable to electrify everything, and so we will need this kind of solution, especially in contexts that are harder to reach, harder to electrify for several context reasons. Michał, any comments?
Thank you. Yes, maybe I will not comment on the technical aspects of presentations, as I don't have a necessary knowledge to go into these very detailed graphs and let's say description of the equipment and processes. But I would like to point out on other thing, as I work mostly on biomass and we see the current let's say discussions about biomass. I think the key for the future of our sector is also to build the positive narratives. And what I mean by this, I think we should also underline the innovative uses of biomass within different, let's say, within different parts of the chain of value chain of the biomass or functioning of the electricity system. So in this regard, the projects you mentioned, and this, let's say, innovative and highly advanced technologically aspects of the CHP, which two projects refer to, are very important, and dissemination of knowledge about such uses should be very high. Also, it is also what we are trying to do, to underline that biomass solutions are advanced technologically, that they provide needed services like grid services, for example, the flexibility, which were mentioned several times, or security of supply, or also they are fit to balance the grid when there is no sun and the wind doesn't blow. So I think this is also a value added. Another thing, of course, is a system integration and increasing energy efficiency, which were also mentioned in both presentations, and also which is the key of the positive impact of CHP on the functioning of the system, from my point of view. And as Alexandra mentioned, the question of prices and electrification. Indeed, we have extremely high prices of electricity in the EU, mostly driven by the price of natural gas. But still, this is a phenomenon which most likely will be recurring in coming years. So still, with current logic of the carbon markets reform, which is in fact positive as it will incorporate polluters pay principle. Nevertheless, the cost of fuels and heat for consumers will grow. So we also, I think, we should underline the cost efficiency and affordability of biomass CHP solutions applied on with different communities and in different levels, whether it will be big CHP units or small CHP units which serve a community, or small industrial unit, and so on. Yeah. So I think the question of price is also the one which should be underlined, and yeah, I really like this different innovative, let's say, aspects of CHP presented by two previous speakers. So I think this is a very important. Not to repeat myself, to build a positive narrative about biomass. Thank you.
Yeah, thank you, Michał. What you said about local communities, I mean, I think it's important, and we shall see if the we know that in RED 2 there has been the introduction of the renewable energy communities. I want to see if this will build something on biomass, if there will be biomass renewable biomass communities, because I think these kind of solutions are very important. We need everything. We need all kind of sustainable solutions, because we don't have much time. So this would be another interesting fact. And then just perhaps another comment on there's a lot of unused biomass, especially agricultural residues, but also other waste streams. But then we know that the main source of biomass currently used is forest biomass. And yeah, we perfectly know the whole debate on the use of sustainable forest biomass, but I would like to recall to many of these people who are against this, that, I mean, a forest needs to be managed, because you cannot leave the forest to grow wildly, because especially in Mediterranean forests, if you let this happen, you have trees growing, consuming the water in the soil, you have the forest gets drier, and then the fire risk increases, and then once you have the fire, you don't have the forest anymore. So you have to manage the forest, you have to thin the wood, and then by thinning the wood, you produce forest biomass, which is sustainable. So we also have to make another effort in explaining this every moment.
Yeah, I fully agree. The problem we are facing, I don't want to use, let's say, not appropriate words, but there is like a lot of misconceptions about biomass. So we still have this vision that there are like as it is called sometimes in some commission documents, whole tree burning. So the idea is that there is a big, beautiful tree and it's used to be
which is not true.
Exactly, it's a value of the wood. Simply no rational owner of the wood, whether state or private, would not sell the commodity for the bioenergy use, which is the least beneficial. Simply we operate on the residues, and there is a price for residues, so no high quality wood would be used for it. And I think there's a lot of misconceptions about it, and we try to work from like PR and communication point of view to spread this knowledge about sustainable practices. But still, there is from my point of view, there is like a lot of misunderstanding around it.
Absolutely.
Maybe from a CHP perspective as well, we do see a trend towards smaller scale applications. So it's not anymore so common that you have I don't know, 20-30 gigawatt CHP plant, because of course in the future CHP is going towards providing more flexibility services, so it will be running less time but in a more flexible way. And so we see a move towards smaller but integrated CHP systems, so used in a modular way, even at district heating level, where the CHP is basically ramped up either as 5 units or 10 units or up to 20 units. And then for on-site CHP, there is this value of demand-side capacity, which is very important for the energy system. So you have long-term capacity that is there, which can ramp up and down if needed. And if that electricity produced on site was not produced on site, then it would have to be produced off-site in a large-scale plant. So that also has this has some value from our perspective.
Sure. Athanase and Nicola, if you have the comments, then we can close.
Just one in continuation of what was said, my final slides with the profitability index parameter. One of the key parameters, as I said, is the market, the price of the energy. So, and of course, if we are in a world where energy price, electricity price is doubled, of course, this gives a strong momentum to the smart CHP or any type of cogeneration fed by biomass. This decorrelate completely from the energy markets, from the fossil energy markets, the price, which is interesting, and it has to be further exploited.
I agree on what has been said so far. I agree also on the kind of size of the CHP system, that should be not big. I mean, it should be have a short value chain, and of course, the two technology, I don't see that one is, let's say, just talking about pyrolysis and gasification, that what we are showing today. I think that they are complementary, because probably the pyrolysis, just that's a personal opinion, but the pyrolysis probably is more focused on the small scale, and they can have a decentralized system for production, while gasification probably is more focused on local production, but also have a lot of promisings related to, for example, flexibility, because just to give a point, of course, oil is more flexible because you can use the standard system of transportation and so on. The gasification have produce a syngas that actually is mainly hydrogen and carbon monoxide, and hydrogen can be used as a storage of energy, so as vector. So these also could give to the system an higher flexibility, maybe more focused probably, instead of the pyrolysis in domestic use, more focused maybe on industrial area, where you have, for example, sawmill or something, that you have to valorize those residues of wood that just are burned. So that's again my personal opinion, that I guess is in line more or less on what has been said so far.
Okay, I will close the meeting now. Thank you to all the speakers for the very nice discussions we had this morning. So the presentations and the video recording will be available soon. We will send you notifications on the social media and through the BioCOGEN newsletter. Again, register to the newsletter of BioCOGEN to stay updated with the next events and webinars until we will be able to meet in person again without any problems. And thank you again, and see you the next webinar. Bye.